Hi, my name is Katie,
My name is Chris Emeka.
I am Philip Ngo.
and this is our AES project. We implemented 128-bit AES in ECB mode. In Replit, I coded a version of the AES encryption algorithm for one block in hexadecimal. It uses a 128-bit block size, and the code is written in Java. It consists of several functions that perform different parts of the encryption process. I did two versions in Replit. I encoded an encryption version and a decryption version of a single hexadecimal block. Then in IntelliJ, I basically merged these two together, modified the code so it can encrypt and decrypt multiple blocks, and then modified it even more so it can translate text to hexadecimal.
Right. In relation to Q1, implement AES SBox, I wanted to explain what it is. The AES SBox is a component in the Advanced Encryption Standard algorithm. It is a widely used symmetric key encryption algorithm. The SBox is a substitution table that maps each 8-bit input to an 8-bit output. The SBox component is used in the AES algorithms to add confusion to the plain text. The SBox is created using a mathematical function that includes an inverse in the finite field gf to the 8th. This ensures that each input value has a unique output value. The AES SBox will accept an array of values. Those values are used to generate a 16-byte array of substitution values. Those values are then used in the inverse SBox to reduce the original values. The template for the function works as: if the input array is not null, it will process all the values in the input and store the results in the output. If the inverse is true, the inverse SBox will be used to perform substitution instead.
I'll be explaining the shift rows function. The shift rows function takes in a 2D array called state, representing the current state of a 128-bit AES block. The function first shifts the second row of the state 1 byte to the left by assigning the second row to a new array containing its second through fourth elements followed by its first element. Next, the function shifts the third row of the state 2 bytes to the left by assigning the third row to a new array containing its third and fourth elements followed by its first and second elements. Finally, the function shifts the fourth row of the state 3 bytes to the left by assigning the fourth row to a new array containing its fourth element followed by its first through third elements. The function then updates the state array with the shifted rows and returns the updated state. The inverse shift rows function operates exactly like the regular shift rows function, except it shifts the bytes to the right instead of the left. Next, I'll be explaining the mixed columns function. The mixed columns function is a part of the AES encryption algorithm and is used to mix the columns of the state matrix. It takes a 4x4 state matrix as input and returns a new 4x4 state matrix. To begin, the function creates an empty 4x4 matrix to store the output. Then for each column in the state matrix, the function performs the following steps. First, it multiplies the first row of the column by a fixed matrix of constants called the mixing matrix. This is done using a function called multiply, which multiplies each element of the row by the corresponding element in the mixing matrix and then adds up the results. The resulting values are then placed into the first row of the output column. After that, the second, third, and fourth rows of the column are also multiplied by the mixing matrix, but with a different starting value. Specifically, the second row is multiplied by the mixing matrix shifted 1 position to the left. The third row is multiplied by the mixing matrix shifted 2 positions to the left, and the fourth row is multiplied by the mixing matrix shifted 3 positions to the left. The resulting values are then placed into the second, third, and fourth rows of the output column. Once all columns have been processed, the function returns the output matrix. Overall, the mixed columns function is used to provide additional diffusion in the encryption process by ensuring that changes in 1 byte of the state matrix affect multiple bytes in the output ciphertext. Next, I'll be explaining the inverse mixed columns function. The inverse mixed columns function takes a 4x4 matrix titled array as input and then returns a new 4x4 matrix called result after performing the inverse mixed column operation on each column of the input array. How this works: first, a new string array titled temporary array is created to hold temporary values. Then two nested for loops are used to iterate over each element in the input array. For each element in the input array, the result matrix is initialized to 0. Then a variable titled answer is created to hold the final value obtained after all the calculations. Another for loop is used to iterate over each row of the inverse Galois matrix, which is titled inverse Galois. For each row, another for loop is used to iterate over each element in that row. Inside the second for loop, the Galois field multiplication is performed using different GF2 to the 8 values, depending on the corresponding element of the inverse Galois matrix. The value obtained after performing the multiplication is stored into the B value variable. If the B value variable has a length greater than 8, then the Galois field remainder is computed using the irreducible polynomial 100011011. If the B value has a length less than 8, then zeros are appended to the beginning of the string to make its length 8. The B value for each row is then stored into the temporary array. And then once all the elements in a row have been processed, the temporary array is used to calculate the final value for that row. For each bit position in temporary array 0, temporary array 1, temporary array 2, temporary array 3, the values at that position are added and the sum is checked for evenness. If the sum is even, a 0 is appended to the answer variable, and if it's odd, a 1 is appended to the answer variable. The result obtained after all the calculations is then stored in the corresponding position of the result matrix. Once all the elements in the input array have been processed, the result matrix is then returned.
I'm going to implement the key expansion function. The key expansion function is also an important part of the AES algorithm. It takes a 128-bit, 192-bit, or 256-bit as input and expands it into a larger set of round keys. These are used in each round of the AES encryption. The key expansion process generates the initial set and 10 sets of round keys. This equals 16 bytes of data in each set. These are then stored in a 176-byte array. So key expansion is done in 3 general steps. Step 1 is where the original key is taken and processed to generate the first set of round keys. This breaks the key into a 32-bit word, which then can be expanded. The second step involves substitution. This involves the S-box to apply a byte substitution method to each of the 16 bytes in every key round set. Then step 3 involves bitwise operations. Steps like XOR are performed on the bytes in the current round key and previous round keys. This then generates the remaining set of round keys.